Hello everybody. In this section we are going to look into model specification errors and diagnostic testing of these errors. So basically this section deals with what happens if assumption 9 of our classical normal linear regression model is violated. Assumption 9 basically says that the model is correctly specified, and what happens if this assumption is violated. Henry and Richard give us a few criteria which should be satisfied by a good model that which has been chosen for empirical analysis. Let's have a look at these. The first is that they should be data admissible, that is, the predictions made from this model must be logically possible. They should be consistent with theory. Remember, every econometric study, every empirical analysis has to make good economic sense, has to be in agreement with the theory. The model should have weakly exogenous regressors, which basically means that the explanatory variables should be uncorrelated with the error term. They should exhibit parameter constancy, that is, the values of these parameters should be stable over time as well as space. Now, unless this criteria is satisfied, any sort of forecasting or prediction using the model would be very difficult. And like we have discussed over all these classes, forecasting and prediction is a very important use of an econometric model. The model should exhibit data coherency, which means that the residuals that is estimated from the model must be purely random. Remember, in statistics we call this the white noise term. That is where all the regular OLS assumptions of the error term are satisfied, right? The mean should be 0, it should be homoscedastic, and so on. And if you find that you have a model which leads to residuals which are not white noise error terms, remember that it is an indication that there is some sort of specification error that has happened in the model. The final criteria for a good model is that it should be all encompassing. That is, it should be able to include all the rival models. That is, it should be able to explain the results of the rival models as well. In other words, the model should be such that there are no other models that can be an improvement over our selected or chosen econometric model. It should be the best possible. Now, what are the different types of specification errors? We have a sample example over here, which is actually your cubic cost function, where yi is the total cost of production, xi is your output. Now the cubic total cost function has xi and its higher powers, that is output squared, xi square and xi cube, as the additional explanatory variables. Now, based on this example, we are just showing what are the different types of specification errors that can be committed. The first one is omitting a relevant variable. So if instead of this particular model where you have xi square and xi cube as the explanatory variable, if you omit xi cube, then it will be a type of specification error. It is called underfitting a model. Another type of specification error which is possible is to add unnecessary or irrelevant variables to the model. So as you can see here, we have an additional explanatory variable which is xi to the power 4. Just observe here, since each of these models are different, the symbol used for the coefficients is also different. So the original model has beta 1, beta 2, beta 3 and beta 4 and so on. All our misspecified models are using different signs. We have alpha over here and we have lambda over here. Also note that omitting a relevant variable is called underfitting a model, and including an unnecessary or irrelevant or not so important variable into our regression model is called overfitting the model, right? Now, other types of specification errors can be when you're using a wrong functional form. So suppose you should have ideally used a completely linear function, which is what we are saying. Remember, this is my original function where yi is beta 1 plus beta 2 xi plus beta 3 xi square plus beta 4 xi cube and the error term. But I'll commit a model specification error if I use the long functional form and I take the logarithmic form of yi, the dependent variable. So assuming that the beta model with the betas is the true model, if I run this model with the data, I am committing the error of using the wrong functional form. Then very practically important specification error is errors of measurement bias. That is, it often happens that we are not able to observe directly either the y variable or the one or more of our explanatory x variables. You can think of examples. Say we are conducting a study on the total demand for a product. We might want to take into consideration the population the existing population as a factor for it. Say we are trying to estimate the demand for automobiles. Yeah, so automobiles or cars or any specific four-wheeler, if we are trying to estimate the demand for it in the macroeconomic framework, we might want to include the population as an explanatory variable. Okay, it's only a hypothetical example. I don't think it will be so relevant, but for the sake of example, if I want to include population as a variable for every year of the time series, we get accurate population estimates only every decade, because your complete census is run or is carried out only every 10 years. So you will have 2001 figures, you will have 2011 population figures, and for all the years in between you will have to do something called interpolating, right? Using 2001 figure and 2011 figure, you can estimate a growth rate, and then applying that growth rate you can say, okay, if this was the population strength in 2001, approximately 2002 the population will be so and so much, and so on. So there, what we have calculated on the basis of a formula may or may not reflect the actual reality. So you might have a measurement bias there. So that's an example. You can think of several other examples, but we'll discuss them as we go on. But what happens is, when you have a measurement bias, that can interfere with the results of the model, that can interfere with the reliability of the model. We will discuss both the cases. What happens if there is measurement error in the dependent variable, and what happens if there is a measurement error in the independent variable, that is the explanatory variable. Okay. Finally, we also have another type of specification error, which relates to the way the stochastic error term, or UI, if it's a time series, we prefer to use UT, where T represents time. So, of the time series. So, the way the stochastic error UI enters the regression, if there is a misspecification in that, that could also lead to our estimates being not so reliable. Okay, so they've given us an example. Suppose the original model is like this: yi is equal to beta times xi times ui. Now this is linear in parameter, but it is not linear in the variable. You can make this a totally linear function by simply taking log on both the sides, right? In that case, when you take a natural log on both sides, you will get, let me show that. You can write it as log yi, natural log yi, is equal to beta times log xi plus log ui. Okay, so if you have your original model is of this sort, you can always do a natural log transformation and get this into linear in parameters and linear in variables form. And if your ln ui satisfies all the assumptions of the classical linear regression model, you can use your standard OLS procedure to determine beta. Now compare this with if you run this model by mistake. So instead of log ui, which, one second. So like I was saying, if instead your error term enters in this form plus ui, it might not satisfy all the assumptions of CLRM, and you are committing a specification bias or a misspecification error. Another type of specification error, which is not really discussed as much, is when interaction among the regressors is ignored. So interaction would mean that sometimes the regressors come in a multiplicative form, as you can see here. In this model, example model, wi is the hourly wages, the mean hourly wages, and we are looking at what are the factors that affect or determine or influence the hourly wages. So as our explanatory variables, we have education level, we have gender, that is whether you're male or female, and how it will impact the hourly wages that you can earn in the labor market. And you also need to look at a combined influence of education level and gender. The importance of this interactive term is more clear when you go into in-depth analysis of labor studies, okay, studies in the area of labor. This is because beta 2 will measure the impact of education level on the hourly wages, keeping all other factors constant, including gender constant. Beta 3 measures the impact of how difference in gender can affect your hourly wages, keeping all other factors such as education constant. But beta 4 here has a combined influence, represents the combined influence that both these values together have. Now empirically, this interactive form has been very useful in pointing out how when you have males and females in the job market for certain types of jobs, even though they have the same type of education level, it has often been seen in several empirical studies that males with the same level of education are getting higher payment than females with the same level of education. Similarly, it has also been observed that often females with a higher level of education are getting paid lesser than males with a lower level of education. So, for the latter case, the influence will be measured by this interactive term, a product of education as well as gender. And remember, gender here is a dummy variable, a dichotomous variable which will take, dichotomous means it is a dummy variable which will take only two values. One which probably can represent male and a 0 which will represent female, or the other way around, but yeah, it can take only two values, where one value will represent male, the second value will represent female. Education can also be a categorical variable. For example, it could be take a certain value when it's only primary schooling, another value when it is secondary schooling, a third value when it is higher secondary, and maybe fourth value for graduation and higher studies, and so on. Now, among these specification errors, we are going to concentrate on the first two, which is underfitting a model and overfitting a model, and we are also going to take a special look at the errors in measurement bias. Now, the reason I'm concentrating on these type of errors is because the syllabus requires only so much. However, we have more cases that have been discussed in the books that have been given in the reference list. For those who are interested, you can always have a look at that.